random motion is proportional to temperature. So when the temperature gets lower, you get less motion, and you can have systems condense out. So nuclei perform. It took 3 minutes for atomic nuclei to form. So 3 minutes after the Big Bang, atomic nuclei form. Now, this happens all so quickly. I mean, it's unbelievably that quick. And then, but it took 380,000 years for atoms to form. It had to be, the universe had to be cool enough for that to occur. And at that point, the temperature was 10 to the 5th degree Celsius. And then after you have atoms, then of course the gravitational thing will starts pulling these atoms together, and you start forming stars. And around 400 million years after the Big Bang, the first stars started forming. And the temperature is really quite low at that point. It's minus 200 degrees Celsius. And then, of course, in about 1 billion years, galaxies form. And then we are here now at 13.7 billion years after the Big Bang. And this is a model. And now the temperature of space, we're not talking about stars. There are all kinds of stars around which are very high. But if you go to space, what is the temperature of space? It's 2.735 degrees Kelvin. So it's really quite cold. The universe is really quite cold. That's absolute. The other point I want to make is that when we do accelerator physics, at the large accelerator, we are really reproducing the conditions of the very early universe. For example, Fermilab, which basically just closed down its machine, which had a beam energy of about 2 trillion electron volts. That basically reproduced the conditions of the early universe roughly 4 times 10 to the minus 12 seconds after the Big Bang. So basically, it reproduces the universe, the conditions of the universe at a very early stage. Now, the Large Hadron Collider, which has a higher energy formula, will actually sample the conditions at a somewhat earlier stage, probably the order of 10 to the minus 12 seconds. And so basically, when you do these experiments, you get information which you can put as input into these cosmological models, and which basically drive the evolution of the universe. And so that's how both particle physics and cosmology are related in a very close manner. Now, there's something else that's there which has been measured. Because of all the charge that was swirling around in a very early stage, there was a lot of radiation in the universe. It's called background radiation, the background microwave radiation. And it was there in the universe from the very earliest stages. And as the universe expanded, the wavelengths got longer. And these things, this has been measured. And this is really one of the primary things that have been measured, that has been measured, which gives enormously important information about the universe. In fact, you see this curve right here. That's the black body radiation curve gotten from measurements of the microwave radiation in the background. And that is a perfect black body spectrum. It's the most perfect spectrum that anybody's ever achieved in terms of measuring a black body spectrum. And it's actually, the temperature from it is 2.7525. So actually it's been measured to quite a high precision. So this is this is the WMAP satellite. It has 20 differential radiometers to measure the spectrum at different frequencies. It has 5 frequency bands between 20 and 106 gigahertz. And this brought in extremely valuable information about the cosmological model. For example, this is the variation of the temperature in the universe. And the thing which is remarkable is how uniform it is. You'll notice that the color range goes from 200 microkelvin to plus 200, minus 200 microkelvin to plus 200. So the whole range is 400 microkelvin. And this is the range, this is it. So again, one of the surprising aspects of the universe is how uniform it is. And this uniformity gave rise to the so-called inflationary model, which unfortunately is a lecture in itself. But it is now understood in terms of what happened at the very early stages. Now, this is an interesting part of that. So what is the universe made of? And if I take the point of view that E equals mc squared, so I have both energy density in space, in matter in space, and I make them, let's make them all energy equivalent. So the matter I convert to energy, and I have the energy density in space. There are three components to what makes up the universe. There is atomic matter, which we're made of, table made of. Everything you see around us, all the stars are made of. That comprises only 4% of the contents of the universe. There's another component called cold dark matter, and that's 23%. And that's made of some exotic particle that we don't know anything about. It's certainly not atomic matter. It's been shown not to be atomic matter. And there's another part which is called dark energy, which is totally mysterious. We don't know anything about that, essentially. But the point I want to make, and this is for the, when I always talk to students, I say there are a lot of things to understand. But the fact is, we only have any understanding at all of only 4% of the contents of this universe. Isn't that remarkable? And it turns out that dark energy plays an extremely important role in another aspect of the universe, which I'd like to point out. The expansion of the universe, remember I talked about expansion, but the dark energy actually is accelerating expansion. When I was a student, people always said, well, there'd be the big crunch, the expansion would occur, and then it would basically expand out and come back again. That's the way it happened. And then there was the point of view that the expansion would occur and it would asymptotically slow down. But now it appears that this is the curve, the red curve is the curve that comes from the data. And the expansion is accelerating. And the reason for it is really interesting. The reason for it is that this dark energy, which appears to be anti-gravitational, it's actually pushing the universe apart, which is a very surprising thing. And that comes from putting it in the equations of general relativity. And for example, we are here now, and the universe, the Big Bang here is 13.7 billion years before now, and here it is. And about 22 billion years from now, the universe will be about 4 times the size of what it is now. And so that's what's happening. So this corresponds to, ultimately, a very cold and dark universe. But don't worry, it's not going to occur for a long time. So what do we know about the contents? The dark energy, we know nothing. In fact, if you take particle physics and try to make an estimate of what it should be, we're off by 120 orders of magnitude. I mean, that is an immense discrepancy. So we know nothing about it. In fact, the dark energy corresponds to what Einstein called the biggest mistake of his life. Because what happened is when he developed general relativity, he noticed that to keep the universe stable, he had to put a constant in. It was called a cosmological constant. And nobody ever believed it. And then when Hubble found that the universe was expanding, he said, oh my God, it's the biggest mistake in my life. And then it turns out that this is the thing which is driving the acceleration of expansion. So even mistakes sometimes can be correct. So, and what about dark matter? We don't know anything about it. We're trying to create it at for example, the Large Hadron Collider. There are some candidates for it, and we're trying to observe it. And so, and people are trying to observe it in underground laboratories, coming in the cosmic rays. Atomic matter research in the 20th century uncovered the structure of the atom and the structure of the constituents, and that was part of what I talked about yesterday, so I'll go over that very quickly. So let's talk about the structure of matter, just for those who perhaps weren't here. If we have bulk matter, if we want to look at the atom, we have to have a magnification of 100 million. If we want to look at the structure of the nucleus, we have to have another magnification of 100,000. And when the nucleon was first, namely the nucleon, which is either a proton or a neutron, that's a generic term for a proton or neutron, nucleon. The nucleon was found to have other constituents, and one could start seeing the constituents when there was an additional magnification about 20, but now we're looking at it, we're now examining the contents with a magnification of greater of 10,000. So what are the tools for investigating the subatomic world? We have particle accelerators, particle detectors, we do scattering experiments, we probe the particle structure and the forces, we produce new types of particles that existed in the very early universe. And of course, I spoke a little bit about this, but let me just repeat it quickly. Basically, particles could behave like light because of quantum mechanics. They have a wavelength which is equal to Planck's constant over the momentum. The momentum increases with energy. And of course, the smaller the wavelength, the greater magnification you can have in terms of observing the system. So therefore, what you want to do is make, and of course, because of quantum mechanics, all particles have an associated wavelength. And the idea is if you want to make a particle accelerator, you want to make it as energetic as possible to have the greatest possible magnification. And that's the whole point. So again, let me go over this very quickly. There were many particles discovered because of the accelerators and detectors. The particles were organized into families, and unfortunately, they got a little garbled by the thing. But the families are based on the same spin. They were based on the mathematical group SU3. And for those of you who deal with group theory, and it was basically a periodic table of the particles, and it was predictive as well as descriptive. And here's the periodic table. I didn't show the whole thing yesterday, but here is the whole. We had spin 0, spin 1, spin 1/2, spin 3/2, and all these particles were searched for and discovered. In fact, an interesting thing is this particle right here, the delta plus plus, was discovered by Enrico Fermi in 1953. He didn't know it, but the significance of it, it was a very interesting discovery. But in a certain sense, it was the beginning, one of the beginnings of this whole business of looking for these additional types of particles. In fact, I was at the university when he discovered it, and I remember all the discussion about it. And of course, the genesis of the quark model was the following. Why does this scheme work so well? It was found that if you develop triplets, that you could actually build up all these families on a group theoretical way. And the triplets were the following. There were 3 types. There was the up, down, and strange quarks. You all had spin 1/2. You all had fractional charges, up was 2/3, plus 2/3, down minus 1/3, straight minus 1/3. And there are 2 basic types of particles. There's something called baryons, which are the heavy particles. They have to do, for example, the proton, the neutron, or baryons. And they consist of 3 quarks. And the mesons, like the pi meson, the k meson, all these other things, consists of a quark-antiquark system. And for example, as I pointed out yesterday, the proton is a very simple thing. It's just two up quarks and a down quark. In the neutron, it's two down quarks and up quarks. And you can see the symmetry there. And you can see that if you put in the charges, the proton has charge 1, and the neutron has charge 0. And that's the simplicity of the model. But the point was you can make all those groups, all those families in this group. So the quarks are discovered by an MIT SLAC group. They use equivalent very sharp electron microscope to examine the inside of the proton and neutron. The laser accelerated SLAC was used, 20 billion electron volts, and the effect of magnification was 60 billion times greater than with ordinary light. Here's a picture of SLAC I showed it yesterday. Here's a picture of it. Here's a picture of the spectrometers that we used. I described them yesterday. And of course, the whole point is that in the old model of the proton, there would be very little scattering of the electrons because it was a sort of a blob of charge. And in the quark model, you would have little constituents inside, and the electrons could bounce off those constituents at large angles. So if you saw large angle scattering, you know that there were little objects inside the proton and neutron. And here's the measurements, basically. This is the prediction from the old physics. These are the measurements. And you can see there was an enormous difference, factors of 100 to 1,000. And that really got people's attention. And the thing which is interesting here, and for those of you who have worked with Fourier transforms, the scattering process is just a Fourier transform of a physical system. And you see, if you have the Fourier transform of a point is a constant. So if you have a constant, now this is a function of momentum transfer. So if you have a constant, you have something which is sort of point-like. It's very, very tiny. And it turned out it was so tiny that one could not even measure its size. But this indicated without any doubt that there were point-like objects in the proton and neutron. And the point-like constituents were found in 1968. It was found in 71 that these things had spin 1/2. In 1972, comparisons of the electron scattering and neutrino scattering indicated the exact fractional charges of the quark model was in, even though the people who had these enormous doubts had to give up. Now, the results required a new theory. So this was the development of quantum thermodynamics. And the thing which is interesting here is that you could talk about the so-called coupling constant. You probably are familiar with the fine structure constant, which is the coupling constant, which is operative in the electrodynamics. So this is a coupling constant which basically has to do with the so-called strong charge. In other words, there's got to be a source for the strong force. So we call it a strong charge. It has its own coupling constant. And it turned out that this coupling constant actually changed with energy by this theory. And there were two aspects to it. There were two aspects, one called asymptotic freedom and infrared slavery. Now, asymptotic freedom has to do with the idea that when two quarks interact at very high energies, the interaction between them weakens. If you make them interact at low energies, then basically the interaction gets very strong. So when it weakens, it's asymptotic freedom, and when you pull them apart, you have infrared slavery. And I remember many years ago, it was when Poland was still under the Soviet Union. I gave a talk in Poland about this, And the response was, we like asymptotic freedom. We don't like infrared slavery. And I found that very amusing. And of course, the infrared slavery is why you don't find free quarks. They just can't escape. And nobody's ever found a free quark. People look all over the place. So that's the new theory. And the point is if you think about the force is approximately constant as you pull them apart. So the criterion in physics, if you want to have a free particle, you pull it to infinity and the interaction goes to zero. Or the interaction energy goes to zero. And here, if you try to pull these things to infinity, the interaction energy goes to infinity, which is not very good. So that's why you can't have any free quarks. And here's the verification of it. So this has been tested. And you can see it has exactly the behavior that was predicted of logarithm dependence. And now we have 6 different quarks: up, down, strange, charm, bottom, top. The thing which is so remarkable, we call these things now flavors. The quarks have funny business. They come in flavors and colors, and the flavor has to do with the type, and the color has to do with the strong charge. Just as you have positive and negative with the electric charge, and positive and negative will neutralize, right? And so we have 3 types of charge in the quark model. And we call them blue, green, and red. And the point is, if you put them all together, they neutralize them. That's why, for example, a proton in itself has essentially almost no strong charge because it has 3 quarks. Each quark has a different color, and they cancel one another. And when you have protons and neutrons interacting, it's the molecular forces. It's just like an atomic system. An atomic system is neutral, right? But you can still form molecules. It's the same thing with the nucleus. The nucleus is essentially a molecule of protons and neutrons, which are equivalent to the atoms. And it's a great mystery why there is this enormous range of masses. And so now let me tell you what the full story is. And it's a little bit tedious, but I think you can hear it. Because this is what we think is fundamental system. Here are the 6 quarks. They come in 3 families. The top row is charged 2/3. The bottom row is charged -1/3. And they correspond to leptons, which are, this is the electron. This is the muon, which is like a heavy electron. And this is even a heavier electron. And for example, it was very strange when the muon was discovered. The famous physicist Agavi said, "Oh my God, what is the muon to do with anything?" He said, "Who ordered this?" And because it was such a novel, I had no idea what role it played. And then, of course, there are 3 neutrinos, and each neutrino is connected to one of the so-called leptons, one of the heavy electrons. And of course, the only thing that exists, these things decay, and they decay ultimately with this side. And that's the electron that also is part of the atom. And then let's talk about the forces. We have the strong interaction. Now, we have force field, right? And according to quantum mechanics, every field has an associated particle. Okay? And so, if you have the electromagnetic field, you have the photon. Everybody knows about the photon. Here you have the gluon field, and you have something called the gluon. It plays the same role as the photon. Of course, the photon is what you know about. And this is the electromagnetic force having to do with electricity and magnetism. This is the weak force, which has to do with radioactivity. And it has two force carriers called the W and Z bosons, and these end up being very heavy particles. And then there's gravity, which is graviton. Now, the standard model, the thing that we really understand today, has to do with only these. Gravity sitting out by itself. And you can see that the quarks basically have all the forces involved. The leptons have every force except the strong force. And that's all. That's the fundamental structure of matter in terms of current theory. And of course, all stable matter that we're made of consists only of three things: up quarks, down quarks, and left quarks. Now, what about the strength of the forces? This is interesting. If we say the strong force is 1, the electromagnetic field force is about 100 times smaller. And the weak force, and this is for the force between two protons which are separated by 10 to the minus 13 centimeters. Now, I'll say a few things about that. The weak force is really weak. You see, it's 10 to the minus 13. That's why it's called weak. But the gravitational force is incredibly weak, 10 to the minus 38. The thing which is ironic is that the strongest forces in the universe come from gravity, in terms of black holes. And the question is, isn't it ironic that it's the weakest force in nature that gives rise to the strongest forces in existence? And the reason for it is every one of these things basically these two in particular, which basically have to do with stable matter. I won't talk about this here. It doesn't have to do with stable matter. These two things basically have mechanisms that cancel them out. Positive and negative, three colors, they cancel out. There is no such thing as an anti-gravity particle. And therefore, in a black hole, you just keep on assembling matter and matter and matter, and after a while, you assemble so much matter that this gravitational force becomes incredible. You know, it basically can crush anything. And the other thing about that, so there's that aspect. This force is long range, which means basically it has a 1 over r squared dependence. This force cancels out after a few Fermis. And this one is very short range because the particles that basically carry it are very heavy. And gravity also is a long range force. It basically goes as 1 over r squared. Now, the other thing which is interesting is that the strong force decreases with energy, as I told you, but the electromagnetic, weak, and gravitational forces increase with energy. Now, that's an interesting difference. And it gives rise to a point of view and that these forces all converge at a very, very high energy, and in fact may become one force. At very, very high energies, there are indications that all the forces become one force. And as the energy goes down, they become these different forces. And that's one of the things that physicists are studying. Now, the other point I want to make is that we call empty space is not empty. There are all kinds of things happening all the time. Remember I told you there's a field having to do with dark energy. Space is filled with that field. There are also things called vacuum fluctuations. And this is something that's really mind-boggling. Because you see, what happens, what this really means, is that out of nothing, you can get a pair. And then it annihilates again. And then you say, well, hey, that's nutty. You're violating conservation of energy. But remember, the uncertainty principle says that if it occurs over a very, very short time, you can bump that energy up to H. So you have fluctuations which actually have measurable effects. And that's the thing. It's not just something somebody thinks about it, says, oh, this is the way it is, this has consequences. Let me tell you some of the consequences. And of course, there's another field that we can talk about, and that's the Higgs field. I'll talk a little bit about that later. How am I doing for time? Okay. For example, these vacuum fluctuations give rise to something called a casting force. And if you're an engineer trying to design nano machines, you better take these forces into account. Because if you take two plates and separate them by nanometers, in their neutral plates, they have no charges. They are pushed together by the casting force. And this has been measured. So it's not just a theoretical prediction. It's also been observed in the laboratory. Okay, so let me talk about the theoretical developments. Now, this is for those people who are not physicists. I apologize for this, but I was be talking to engineers and physicists, so bear with me for a little while. Electroweak unification occurred in 1967. It relates the electromagnetic force and the weak force, but it required the introduction of the Higgs field. And I'll talk about that. As I told you, quantum thermodynamics was developed in 1973 to describe the forces between quarks. And the combination of these two theories is called a standard model, which is the current model of particle physics and their interactions. The particles and their interactions. And the interesting thing, it's been tested at every accelerator has been in operation, and it's met every test. So it's an extremely good theory, and it's considered one of the great intellectual developments of the latter half of the 20th century. So it's a fantastic theory. Now, so let me talk about electroweak unification. Now you see, consider these processes. A neutrino interacting with a quark. Well, it will interact through the weak force. So if a particle has to be exchanged, it could be the Z particle. If a neutrino interacts with a quark and turns into a muon, it will interact with a W particle. If you have electromagnetic interaction, an electron interacting with a quark will exchange a photon. This theory relates all those three processes. And that's why it's called electroweak unification. However, to do so, it has to introduce something called the Higgs field. And let me explain why. And I think you're probably interested in the Higgs field because there was a lot of publicity about the discovery of the Higgs particle in recent days. And so why do we need a Higgs particle? The point is, when these theories are developed, physicists use symmetry principles. And one of the in this the application of symmetry principles in this problem also involved assuming that all particles in the universe have zero mass. Because of course that's the greatest symmetry, right? If every particle has the same mass, then you can deal with them in a very symmetrical way. However, we know that's not true. So what you do is you make the structure of the theory, and then you introduce a term which breaks that symmetry. And that term is the Higgs field. And let me tell you how that does it. So the idea, oops. Nope. The idea here is that all of space is filled with something called the Higgs field. These massless particles interact with that field, they have an interaction strength, and it's as if these particles are trying to go through molasses. So they basically interact, And the point is that any particle which has zero mass has to have the velocity of light if it's not in the material. And so if you slow down these particles, it's equivalent to giving them mass. So the bigger the interaction of the particle with this Higgs field, the slower it gets, and the larger its mass. And that's it. And so the idea is that in addition to all the other things that are in the vacuum, there's a Higgs field which basically interacts with particles and gives them mass. One of the things that physicists have always had trouble with is where does mass come from? And this is one of the mechanisms that people have proposed. But the question is, of course, is it true? But the other thing is, the thing which is very interesting here now, and this is where the physics is so beautiful. If I have for example, an electron interacting with a quark, I can exchange, for example, a Z0 particle or a photon or whatever. And the point is that I can get something called a virtual process. It's like a vacuum fluctuations, that this Z0 will go into a top anti-top pair. But it only lasts for a very short time, and it becomes a Z0 again, because again, you can't violate the uncertainty principle. And I can do that here. I can do that here. And in one case, I can actually have a Higgs particle. Of course, there has to be a Higgs particle associated with the Higgs field. It can be one of the virtual states, one of the virtual transitions. And if that happens, it will change the scattering probabilities. That will give rise to corrections. And those corrections can be calculated. Okay? They can be calculated. So therefore, if you make a measurement of that process, you can go backwards and find the mass of the thing which is making that correction. Is that clear to people? Is there any confusion over that? And that's very powerful. And this is how the corrections go. And so the point is, how did this work? How well did it work? Let me point out something. It took a long time to discover the top quark to get its mass. Long before it was discovered, there were measurements done, and starting in 1990, going up to this point right here. And this is trying to get the mass of the top quark from those calculations. And as the precision was bad, the error was quite large. As time went on, the precision got better and better and better. And finally it went down to here. And this is the prediction for the top mass. These dotted lines correspond to the actual discovery of the top particle and its mass. And you see how well they correspond, the indirect measurement and the direct measurement. And that gives you an idea of how good that theory is. And so the top mass was predicted long before it was actually discovered. And as I said, the same thing was done for the Higgs mass. It was harder because it came in a somewhat different way. But here, this is a so-called chi-squared. The minimum is where you expect the mass to be. And there's a statistical uncertainty, so basically the mass could be anywhere sort of, it should be, with 68% probability, it could be anywhere from here to here. Okay? And so those things, the Higgs mass was predicted in a certain range. However, again, this was such a far off theory in a certain sense that one had to look for the Higgs, and the Large Hadron Collider was needed to search for the Higgs particle. Let's go into that. before I do that, I want to make a point. I've already told you that accelerators are powerful microscopes. Oops. This is what I hate about these things. All right, well, the fixed target accelerators are powerful microscopes. And the way they were initially used is that you have a particle hitting a target, and you produce a particle. However, remember I told you that to get the smallest wavelength possible, you have to have the most energy available in the process. Now, in the fixed target regime, the energy available only goes as the square root of the beam energy. And why is that? The reason for that is because in the process, you have to conserve momentum. And when you conserve momentum, you can't use all the energy that you have available. So while these are great microscopes, they have their limitations. In fact, the SLAC experiment was basically a fixed target microscope. What is a better microscope is this. Oops. Colliders. You see, in a collider, you have two equal energy beams coming in, and they collide. Since the total momentum in the initial state is zero, you have to give no energy up to momentum conservation. And the amount of energy you have available, instead of being the square root of E, is 2E. And that's why today, if one is going to build an accelerator, one will never build a fixed target accelerator. Only colliders are being built. And that's why the Large Hadron Collider is the machine that is being used to advance physics. So let's talk about that. This is a Large Hadron. It's an accelerator which is 27 kilometers in circumference. It's a proton-proton collider. The design specification will be 14 trillion electron volts available for the measurement. And you can see how it works. Those are the beams going around, colliding where the detectors are. Now, of course, this exaggerates it. The actual machine is only about 100 meters below the surface. But, so you can actually see what happens there. Here's what it looks like underneath the surface. It has thousands of superconducting magnets. It has the largest, coldest spot in the universe. Basically, the superconducting magnets are cooled down to 1.92 degrees Kelvin. Remember I told you the universe was 2.75. And this is an enormously sophisticated accelerator. Here's one of the detectors. This detector is the Atlas detector. It is 46 meters long, 25 meters in diameter, and weighs 7,000 tons. 25 meters in diameter means that essentially it's equivalent to the height of a 7-story building. And it's an amazingly complicated device, and I'll talk a little bit about that. And if you try to get a person in perspective, you can barely see that person. Here is the so-called compact muon detector. It's a solenoid detector. This is the small one. It's 21 meters long, 15 meters in diameter. It weighs 12,500 tons. Again, you see a person standing there. Let's see, let me see. No. It's just there. Okay, here are the detector responses. They have a number of chambers in them. And the point is you want to distinguish electrons from muons, photon, from a hadron, from a neutrino, and there are different ways, different schemes of doing it. And you can see that each particle has a different behavior in the array of detectors, so you can actually distinguish them. Except for the neutrino, with the neutrino you don't see anything, except that you lose transverse momentum. And you detect it by trying to conserve transverse momentum. If you can't conserve it, then basically you know that some neutral particle has escaped that is not interacting with the calorimeters. Now, here is a two-jet event. This is one of the simpler events that you get. And this is actually what occurs. This is a simulation of what occurs. This is a very simple event. And the point I want to make is there are 1 billion events like this, or even more complicated, per second that occur in these detectors. And of that, you only want to save 100 events. So you have to do real-time discrimination against the events that you don't want. You've got to do it on the basis of topology, energies of the tracks, the number of tracks, etc. And it's an extremely formidable calculational task. And I point this out to you because many of you are engineers, and you can appreciate what kind of technology is required to do that. Okay, so let's talk about the major challenges of these detectors. Each of these detectors has about 100 million readout channels. The collisions occur every 25 nanoseconds. So you have to be able to actually gather that information in very, very short times. For example, Atlas uses over 3,000 kilometers of cable just to cable it up. You can see what a job that was to get that thing together. The data volume recorded at the front end of CMS is equivalent to the worldwide communication network traffic. That's the amount of information that's taken in by this detector, and it's in operation. And one of the great worries about this accelerator is that the beam is extremely powerful and has so much energy in it. And the kinetic energy of the beam is that of a 10,000-ton ship going 20 miles per hour. So if you missteer that beam, it destroys anything in its path. So the feedback systems and the control loops have to be so redundant and so carefully planned that you never have this possibility. Now, I just want to say how daunting these things and how big these things are. Here is the object. Here's the weight in tons. I think it's sort of confusing to see this comparison. A 747 is only 200 tons. The Endeavour Space Shuttle, 368 tons. The Atlas detector is 7,000 tons. The Eiffel Tower, believe it or not, is only 7,300 tons. And the USS John McCain, which is, I think, a destroyer, has 8,300 tons. And CMS detector, which is the small one, has 12,500 tons. So it's really small, but it's compact and heavy. And here's a computing challenge. The LHC will produce 10 petabytes of data every year. This data has to be stored, processed, and accessible all over the world because the groups working on this detector are scattered all over the world. The grid will consist of 100,000 computers and multi-massive data storage devices. The grid is a pure system spreading across the world. And I want to point out that in the process of preparing for this sort of thing, actually CERN invented the World Wide Web. I don't know whether that's well known, but the World Wide Web came from particle physics. It was an attempt from a bunch of physicists who wanted to share data and share analyses across the world. And here is the grid system. Here is the central laboratory. The data will go to various laboratories across the world. And then at various universities, this is the second year, they will all be able to communicate with one another and share data and share analyses. It really tells you about how global science has become. It's totally international. The idea of having national science of this caliber, of this magnitude, doesn't exist. Now I want to talk about does the Higgs particle exist? This is something that has to be done. You want to calculate. You know, you have a Higgs field, which has to do the job I told you about. There's an associated particle with it. You would actually calculate what that particle will decay in as a function of its mass. This is what it is. Here is the mass of the Higgs particle, and here is various decay modes. Here goes to a tau plus, a tau minus, which is these two leptons, a V bar, two quarks, ZZ, WW, top, and each of these curves is calculated. And the idea is you look, you get your data, and you look for the decay products that are here. And you see whether you see any bumps. And so let me show you. Here's a clearance, for example. The Higgs going to 2 gamma rays. And here's the background, and this little bump will stop. If you look at it carefully, this is it. Now that's only one channel. There are many other channels that want to look, and here's another channel. And this is the Higgs going into 4 muons. And you can see there's a very healthy peak here. And then you can take all the channels and put them together, and when you do that, you get some sort of probability function that you put in. And this is it. This is from the atlas. And this is the Higgs discovery line. And here it is, putting the channels together. And the mass is around 126 billion electron volts. So the Higgs does exist. And now the question is whether it's the standard model Higgs or it's a different kind of Higgs. That's what they're trying to examine right now. But the point is, it implies that there's a new field in the universe which basically is giving particles their mass. So the Large Hadron Collider is addressing a number of these questions. So let's go through them quickly. Okay, I can move on. Okay, the first one are the new symmetries, new fields, new laws of physics. The Higgs has been discovered. People are now looking for supersymmetry. This is supersymmetry is a mirror set of fundamental particles that supposedly exist in the universe. This set of particles is required to unify quantum theory and general relativity. And it has some other functions within particle physics, which are too abstruse to discuss right now. But people are looking for supersymmetry. And supersymmetry means, you have the so-called fermions, which basically have spin 1/2, spin 3/2, spin 5/2, etc. Or you have the bosons, which are integral spin. So the idea in supersymmetry is that every fermion has an associated boson, which is very much like it, to be a slightly different mass. But that's the idea. So for example, an electron, spin 1/2, has a selectron, spin 0, etc. A gluon, spin 1, has a gluino, spin 0. And that's what it is. So people are looking for that. Second thing, do the forces become one of high energy? I mentioned that already. What is dark matter? And we produce it at an accelerator, at the LHC. And of course, it turns out that one of the supersymmetric particles is a great candidate for dark matter. So that's also being searched for. are there extra dimensions of space? Now, that's an interesting question. You know, in string theory, which makes an attempt to unify, again, gravity and quantum theory, it turns out that your theory has to be in 10 dimensions. So basically, so what you have 6 extra space dimensions. You have 3 ordinary ones, x, y, z, plus time, which is 4, plus 6 extra space dimensions. That seems kind of crazy, right? I mean, however, in this theory, the reason it isn't crazy is because in this theory, those extra dimensions roll up in distance of 10 to the minus 32 centimeters. So they basically disappear. There's no way that you would ever have any recognition of any effect in everyday life from these extra dimensions. However, in some theories, they propose that some of these extra dimensions could go out as far as 10 to the minus 18 centimeters. And if that's the case, you can actually observe the effects at an accelerator, at the LHC. So we basically, can we learn anything new about dark energy? That's also a question. Are quarks the smallest building blocks of matter? Another question, which I discussed yesterday. There'll be all kinds of breakthroughs that will come with the Large Hadron Collider, and also new space probes and astronomical probes. And so actually, this is an extremely exciting time in physics and cosmology. And I think there'll be some really revolutionary things coming up in the next 5 or 10 years. Thank you very much.